Every time you flip on a light switch, you're plugging into this enormous, really complex economic machine. So today, we're going to go behind the scenes and look at the real economics of generating power. And I think you're going to be surprised at what actually drives the cost of the electricity you use every day.
So let's just start with what seems like a pretty simple question, right? What's the main goal of a power plant? Now, your first thought is probably to generate electricity as efficiently as possible, to get every single bit of energy out of the fuel. And that makes perfect sense, but it's not actually the whole story.
The real goal, when you get right down to it, isn't about peak efficiency. It's about peak economy. See, profit is the #1 criteria. And that little detail, it completely changes how we have to think about power. Efficiency is, well, it's just one part of a much bigger financial puzzle. The real name of the game is making power at the absolute lowest cost for every single unit.
Okay, so how do these power companies figure out that lowest possible cost? Well, it pretty much all boils down to one single fundamental equation that runs the entire industry.
And there it is. Looks pretty simple, doesn't it? But trust me, everything we're about to talk about comes from this basic idea. The total cost to make electricity is always a combination of two really different kinds of expenses: fixed costs and operating costs. So let's break them down. First up, you've got your fixed costs. The easiest way to think about this is like the mortgage on the power plant. It's that huge upfront investment you have to make. The land, the buildings, the giant turbines and generators. And on top of that, you've got the interest on the loans, taxes, insurance. And here's the kicker. You have to pay all of that whether you're running at full blast or not generating a single watt. And then, on the other side of that equation, you have the operating costs. So if the fixed costs are the mortgage, think of these as your monthly utility bills. This is the stuff that changes: the fuel you burn, the salaries for the people running the place, and all the maintenance to keep it going. And the key thing here is that these costs go up or down depending on how much electricity you're actually making.
Let's look at a real-world example, say for a typical steam power station. When you actually break down where the money goes, it's pretty eye-opening. You've got fuel at 40%, then operation and maintenance at 10%. Add those up and you get 50%. So where's the other half? Well, a full 50% of the cost is just those fixed charges, that giant mortgage payment we talked about. This is exactly why focusing only on fuel efficiency misses half the story.
So, knowing all this, how do planners decide what kind of power plant to build in the first place? Well, it all comes down to this incredible, high-stakes balancing act between those fixed and operating costs.
In this table here, it shows that trade-off perfectly. Look at your options. You could build a big hydro dam or a nuclear plant. The upfront fixed costs, they're massive, but their fuel costs, their running costs, are super low or even free. Or you could go the other way and build a diesel plant. It's way cheaper to build, but the cost of fuel to actually run it is through the roof. Every choice is a totally different economic bet.
Which, of course, brings up the million-dollar question, or I guess the billion-dollar question. If you've just spent all that money on a huge nuclear or hydro plant with these giant fixed costs you have to pay no matter what, how on earth do you make that plant economical and produce cheap electricity?
The answer, and this is probably one of the most important concepts in the entire power industry, is something called the load factor. All it is really is a measure of how much a power plant is actually being used compared to its total potential. So a plant that's running all the time has a high load factor. One that only kicks on for a few hours a day, that's a really low one.
And that's a huge problem, because our demand for power is anything but steady. I mean, look at this load curve. Demand shoots up during the day when everyone's at work and businesses are running, and then it just plummets in the middle of the night when we're all asleep. Managing this wild swing in demand is the single biggest challenge the grid has to solve, every minute of every day.
And here it is. This is the big payoff. The higher the load factor, the cheaper the electricity. It's that simple. Why? Because you're spreading those enormous fixed costs, that giant mortgage payment, over way more kilowatt hours of energy. The more you run the plant, the less each one of those kilowatt hours costs to make. A low load factor, on the other hand, means you're going to have really expensive electricity.
And that leads us to the core strategy of the entire power grid. To make those super expensive hydro and nuclear plants pay off, you have to run them all the time, non-stop. They become what are called baseload plants, providing that constant minimum amount of power the grid always needs. This pushes their load factor way up, spreads out those fixed costs, and makes them incredibly cheap to run on a per-unit basis. Then you can use other plants, like diesel, that are quick to start up to handle those peaks in demand. So,
After all of this, what does all this complicated economics and engineering actually mean for you? Well, it's all hiding in plain sight, right there on your monthly electric bill.
All right, so let's just recap the secrets we've uncovered here. First, the main goal is always the most economical power, not just the most efficient. Second, that whole economic picture is driven by one simple equation. Total cost equals fixed costs plus operating costs. Third, picking a plant is always a strategic balancing act between those two costs. And finally, the secret weapon that makes it all work is a high load factor, running those big, expensive plants as much as humanly possible to drive down the cost of every single kilowatt.
And that leaves us with one last thing to think about. Renewables, right? Solar and wind, they fit this model perfectly. They have really high fixed costs to build, but their fuel, the sun, the wind, is completely free. So based on everything we just went over, how do you think their natural variability changes this whole economic equation for the grid of the future? That's the challenge ahead. Thanks for joining The Explainer.